class early. Okay? Yeah. Put your cell phone aside, all right? Okay. Focus your mind on the course, on the class. Okay, that's very important because those techniques you need it. You need it. Okay. You hope that when in the future you have a good job, but all the good job have a good, very big challenge for you. If you have much knowledge to deal with it, you will feel very happy every day. If you don't have the knowledge, you'll find it's big challenge. It's torture every day for you. So you will say, I wanted to work at TSMC. Okay, good. You have good opportunity to enter the TSMC. But you also have a higher risk that you will be fired by TSMC next year. Okay, that's because you have to get the sufficient knowledge to deal with everyday challenge in the work. Okay, there is not a routine work. Okay, high pay, high risk, high challenge. Okay. Like my daughter, okay, he works in the Tesla, okay. Now he is studying in the MIT, okay. Big change. High pay. You say TSMC is high pay, but your Tesla about 3 times of the TSMC. High pay, of course, but every day is just high risk, high challenge. Which one you want? Think about it. All right? So this is, you want something, but you have to pay attention to your task. You have to do your effort, which is worth for your pay. 你的工作能力一定要跟你的 pay match. Okay. So that is we use the theoretical model. It may be boring, but it's just powerful to obtain something you need. If you do experiment, you do nothing. You do nothing. Okay. But if you develop the theoretical model, you can get something your company needed or your research needed. So this is why we developed the theoretical model for the mechanism of the same thing. Nobody wanted it, but you have to do it because you need your value is trustable, it's reliable data. So we adopted the W maxima is this one, right? But the purpose is just that we wanted to determine the stress and the strain. We got the P and the H. P is load, H is indentation depth. They are useless. 它们是没用的。So how the load transfer to be the stress, and then we have the indentation depth transfer to be the strain. If stress and strain are available, then you can determine a lot of, you can determine material property. All the material property, they are defined in terms of stress and strain, rather than the load and the depth. Singular. Okay, single. Another is just we can evaluate the different strain energy. The strain energy, beyond this strain energy, I believe that you have some kind of the defect, 缺陷, take place in your sampling. Okay, all right? Like Samsung developed the IC chip, and then TSMC also developed the same chip. You find that Samsung just have the mechanical defect. So there's high resistance, high resistivity. So it's just a powerful consumption. Power consumption is high, so they cannot compete with the TSMC product. Because in the same field, within the same field, they have a lot of the defect they cannot solve. Okay, so this is a real case. This is not a story. Okay, it's a real case. Okay, so in the competition of the TSMC in chip, I think how to solve your problem, solve all the defect in your microstructure become very important. Very important. Otherwise, just you prepare the chip, but your ability or your capacity or every performance is not good. Not good. It's inferior with other people's. So this is a big challenge. There's a strong competition. Okay. So this is A of 10 equation. Now, we want to determine the stress-strain equation. Now we determine the strain force. The strain within the composite field， 在薄膜里面的一个应变。Let me talk about the first definition of the strain. Okay. Let me talk about the definition of the strain. This material with the constant coefficient, this constant coefficient maybe the coefficient is just a rectangle, okay? Like this. And then apply the load, P. Other two side. Allow this material have a tension, have a tension outside. Okay? Or you can use this constant cross-section, maybe circular cross-section. This is constant cross-section, it's in rectangular form. This is circular form, right? You prepare your specimen, it look like this one, and then you apply the P on the two ends of your sample. Originally, you have the length. Your sample original length before you apply the load is we call the L. Then if you apply the load, you have the length change. We call the delta L. Right. And then the cross section, either this rectangular form, maybe it is circular cross section. All right, but we apply the same load. We originally have this length. And after apply the load, we have the extension of your sample with the delta L. This is one dimension. Delta L or L, we call the definition. This is true. So strain, this length unit, this is also length unit. So our strength, no unit. So strength, no unit. You will graduate, in the future, you will graduate from the AS NCKU. You cannot make any something joking that some people ask you, what is the strength definition? You cannot answer, or your answer is wrong. Because you are the student, is at high level. Okay. Some people ask you, give you the pay, is relatively high compared with other school, other campus. Okay. So strength, no unit. Right. But your sample should be the constant cross-section. In our case, we use this model. We single out the sample. Our sample is just complicated because it's made of the some layer of the same pin. But we can simplify it to be the rectangular sample in the rectangular form, and apply the load up to side, and to obtain the strength. Okay, now let me develop the strength first. Here is the indentation depth. Here is the indented cavity. 这个压痕的痕迹。Other the bottom pole, other the bottom pole, to this is just other the height. This height we give it the HC. HC just the W maximum. W maximum, like the formula we described in last PowerPoint. Okay. So other this central point, this is a regular triangle. Because we use the Bokovich indenter, so the cross section of this triangle is a regular triangle, the 正三角形. Out of the center of this triangle, out of the bottom here, we have from here to here, the length is just the real contact depth, just as we obtain from the W maximum. Okay, W maximum equal to HC, like the last equation we showed. Here, we have the cavity, we have the vacancy. 这地方是空的. This volume of this vacancy can be divided into three portions. Because each side are with the same length. Each side with the same length. The length is just this value. If you have a HC, then the side length is just this value. Alpha is just the fixed angle, right? Okay. Now, this cavity volume, 这个空的这个地方的体积 can be divided into three portions. One of the three portions is just this gray area, 灰色的地带. This gray area is just the triangle volume. Is 1/3 of the total cavity volume. Alright? Okay. This value allow it is equal to be this rectangular form. Why we have this volume equal to this one? Because we want to define this epsilon to be our sample in general. Is define our sample to be the constant cross section. So allow this gray area, this gray volume area is just created by real case. But with single data, this volume equal to this rectangular volume, rectangular body volume. This volume, how the thickness, this thickness is d theta. This d theta is created, how this rectangular volume equal to this triangular volume. Okay, all right? The thickness is just your thin film thickness. Okay? And the side is just the one side length of this regular triangle. First this one. This data times this one times this thickness. This volume equal to this gray volume. All right. We change this cavity in the indentation real case to be assumed to be look like the rectangular power is an extension. This extension with the length change we call the d theta, just like this one, delta L. Right? This delta L just we applied the load, then we created this rectangular plate, power extension outward with this length. We call d delta L. This delta L just means like the d theta. Nevertheless, just this rectangular volume equal to this gray area. So from this one, then we can determine d theta. Okay? So how to determine this one? This VI is just the 1/3 of the cavity region, just the gray area is this volume. This volume is 1/3 of the total volume. The total volume is V indented. This is just the total volume is V indented. But this gray area is 1/3 of the total volume is this value. Okay, we have the detail up here. This is just this rectangular frame. Okay, and then this V indented is this value. Is just this one. We have the height, and then we have the cross section is just a rectangular triangle. Okay, no, regular triangle, and then we have the height is just a C. Okay, so this total volume is this one. So we have the total volume is this value. This value is put here. Then from this equal to this one, we can determine our d data is this value. Okay, so in the meantime, I'll ask you how to determine it. Okay, because this real case is not a rectangular compression or tension, but we change it from the volume equivalence. This volume equal to the constant cross-section volume in this rectangular volume. Okay. So in this case, this equivalence of these two volumes allow us to determine the equivalent tension length. We call this data, D data. Okay. So this is from this one. And then now we have the numerator. This is the denominator. Right? This is denominator, 分子. We have the numerator. Numerator is 分母. The numerator, how to do this? Is this rectangular color? This rectangular color, we have the 1/3 of the regular triangle area. This OBC is equal to OBC, right? But the numerator is created by this color, rather than this one. This is created by our indentation. But it is associated with this volume. This volume is just the rectangular, triangle color, triangle color. So this triangle color, we have the three-sided length, and then we have the total length. This total length, we call it T. So this color, triangle color, all right, we can obtain this value. This rectangular color, that is to be the rectangular plate, okay? This color, okay, our real volume is created in this form, but it is associated with this color. This color is just used to create this volume, okay? So it is just mean that this color is associated with this cavity volume, all right? So this denominator, how the triangular color, this triangular color, how it is volume equal to the rectangular volume with the thickness is theta, okay? D theta is related to this value, but this theta is rectangular, this color, triangular color, all right? So it is used as a numerator. Numerator is 分母, d theta is 分子, okay? So from this equation, we can determine the denominator. Denominator, 分子, is d theta. Okay, this is related to this cavity volume. But this rectangular, triangular column changes to be the rectangular volume. This rectangular volume with the thickness. This thickness is used as the numerator, 用作的分母. d theta or d theta, from the definition, in the constant cross-section, because our constant cross-section is just a rectangular constant cross-section. This rectangular constant cross-section allows us to define our strength. Our strength is just d theta or theta is our strength. So the equivalent of strength in this cavity region, can be obtained from this equation. This equation, d theta is available from this equation, and then theta is from this equation. Okay, so you have to when you back home, you have to understand, to review the material, how to obtain the d theta. It's just this rectangular volume equal to 1/3 of the capital region. Okay, and then this portion is related to this side, and then this 1/3 of this portion is just related to this side. Okay, so we'll just take one side. That's enough. All right. So our D data over data is just from the analysis of these two plots. Okay, we can obtain our action. This equation very, very important. Why? You have your H and the P plot. You have your load and the depth profile. From the slope of the analysis, we can obtain the HC. Or from our theoretical model, we also obtain the HC. We have a HI. Then HI is available, then we can obtain the HC. So HC is available. So HC is the relation to our HI. HI is just our indentation depth. T star is the total phase thickness is available. So first, this equation. This equation allows us to determine our strength as function of our indentation depth. Okay. If our indentation depth is available, you can determine HC. You can determine HC, use this equation. Then you can transfer your indentation depth to be the strength. Okay? So in the midterm, I ask you, what is the mean by this equation? Okay, this equation allows you to know how your output change it to be the strength. Then you can use the next step. You determine your load to be the stress. Here is just our indentation depth transfer to be the strength. So that's this equation in the indentation is the popular use. Okay, but it is developed by our labor. Okay, you find it's very useful. Okay, so originally your experiment data, your measurement, you obtain some of the data is not used, is useless. But from the formula we develop, we can change our indentation depth to be our strength first. Now we turn to the stress and our load. Here, let me forward to here. Okay, we want to strength our develop. Okay, now we want to develop the stress within the same field. Okay, same field behavior is strongly dependent on the stress and the strength arising in the same field. Okay， 你的薄膜的一些所有性质跟你的应力应变发生在这个薄膜里面息息相关。Okay, so we want to use from the narrow indentation test, we try to understand what is the stress and the strength distributed in our same field, Okay, we want to obtain stress and strength. If stress and strength are variable, then you can determine the material property or mechanical property. And also you can determine different criteria like the strain energy. Okay, strain energy. That's very, very useful. That is why we spend much time to do it. All right. Now, we want to determine the stress. We define it, we call it strain energy. Like I will mention above. Right? Stress. If stress is available, strain is obtained now, then we will have an integration over the work zone. In the work zone, maybe in this some of the fixed area, and then we have a stress and strain. We give the times of the stress and strain, and then give the total volume integration. Here, dVi is just 1/3 of the cavity, so we have the three times because dVi is just 1/3 of the total volume change. Okay, so here we have 3 times because we want to determine the total of the strain energy. So we have 3 times of this one. We call the U1. And then another viewpoint, we can use the work. Please change the P to be the small p. Okay, this capital P change it to be small p. Okay. capital P, change it to be small p here, please. Okay? So this is not a law. This is pressure. Pressure times area is force. Force times the distance is just the energy, right? Force times the distance is just the walk. So here, not a law, is pressure. Pressure times a force. Force times the dz. Dz is the downward, all right? Is distance, so it's a walk. So from the walk viewpoint, we can define this walk. This walk should be equal to the strain energy, right? Should be equal, all right? Because the unit is the same. This is just we talk about the same thing, but with different viewpoint, right? One viewpoint is from the definition of the stress and the strain, and another point is just the P. P is just the load or the pressure you apply, right? So this we have 2 points. So if we have this equal, because the dV in the indentation is just 3 times of the VI, right? V indentation. Equal 3 times the VI. Okay. So you will find that the integration for the dV is the same for this equation equal to this one. So from this one equal to this one, we'll obtain this one. So first the P. P is just your stress and the strain times together equal to your P. Your small p, what is P? Is the contact pressure you apply. Okay. But when you how carry out your indentation, you give your force load is capital P. But small p and the capital P, they have a relationship. What is the P? This small p, just this. Okay. So action I, you have obtained. Now you want to determine the sigma I, stress. If stress and strain are available, they time together obtain your small p. The small p is just a uniform distributed contact pressure. Alright? So this is we obtain this one. Alright? Okay. This equation will give the B. Okay. And then A and B, we want to obtain the internal stress within the same field. And then we can use the Fuchs law. Internal stress and the strain. This is internal stress and the strain. They have the Young's module for the same field, for the composite field. Alright? There's a Fuchs law tell us we have the relationship, we have the equilibrium look like this one. So we combine these two, and then we will develop, finally develop this one. So combine this and this equation, we will determine the internal stress. And then the detail we'll talk about it later. Talk about the next time. Okay, how to use these two equations to develop this one. This equation is very important. First, FC. FC is just a load we apply. The load is a known value. You apply it, you give this load capital P. This P, HC is the real contact depth. You can obtain from your measurement. And the total fin thickness T star is also variable. From this equation, you will find that your internal stress is the relation your load applied. So this equation is also very important in the normal integration testing. You know the load you apply. Through this equation, you can determine the internal stress in your same field. So the last equation allows you to determine the total indentation depth, and then you determine your strain. And then this equation, you can, if you know the load from this equation, you can determine the internal stress from this equation. So they are very powerful. Okay? These two equations developed by my lab, but I think it's very useful in the future when you give the indentation test. You can use it without any problem because I have checked many cases. If yes, this is true. Okay. All right? So if internal stress and strain are available, then we can define many things. We can use the relationship to find many properties. So The more detail I'll tell you next time. But from these two equations, how to obtain, I will give the derivation next time in the blackboard. Okay, right? So we stop here today. I think most people are tired. Okay, you have to focus your mind, or not just okay. Because you missed this opportunity. Maybe you missed a lot of time in your future. Okay, you have to value all the class and then the material in the class. That's very important. That's my advice. Okay, because you have a long way for your life, okay, for your future. Okay. So we stop here.